Okay, so first of all, does anyone have any questions about the lecture videos or the vector notes? Um, Anything that was unclear in those? Okay, once we get going, I'm going to give a little, like, sort of Cliff Notes type summary of that stuff. Um, but if you haven't watched those videos yet or anything like that, it's important that you do because there's a lot more detail in those than what I'm going to say. Um, and then what about the assigned problems? Anybody have any assigned problems that you'd like to see me go over? I'd be happy to do a couple. Nope. Okay. Well, let me just give a little spiel about um, particle statics and try to emphasize the main points. And then we'll just get into a bunch of example problems and problems for you to work on so we can just kind of all get straight on this stuff. Okay, so we're getting into particle statics. Um, and the statics part means that um, accelerations of the body's center of mass are zero. And that once we start talking about rigid bodies, the angular accelerations of bodies are zero. And so what that means for Newton's second law is that Newton's second law, N2L, Newton's second law, just becomes add up all the forces on a body, they have to equal zero. If they're not equal to zero, there's going to be acceleration. Okay, so this is what we're going to use over and over again. F net means the sum of all force vectors acting on the chosen body. And this idea of the chosen body is going to be really important. We're going to have to be very clear to ourselves about what's included in our chosen body and what's excluded. Okay. Also, the sum of all forces being equal to zero does not mean that each individual force is zero. It doesn't mean that no forces are acting on the body. It just means if you add up all those vectors, they add up to zero. So like everything sitting on this table right now has a net force of zero. But they all have forces acting on them. They all have gravity acting on them, a normal force. Okay, it's just that those force vectors add up to zero. One thing, this isn't going to be an issue in statics. It's an issue in dynamics. Newton's second law generally only holds if your coordinate system is inertial. And an inertial coordinate system is one that is not accelerating. The origin isn't accelerating. And the orientation of the axes is not changing. So if either of those two things are happening, you can't use Newton's second law. It won't hold. Okay. So like if you think of a coordinate system as like a video camera that's videoing everything, okay, where that camera is mounted, think of that as the origin location. If that video camera is accelerating around, the measurements it takes are going to look like they violate Newton's second law. Okay. And so actually, like a whole category of funny videos on YouTube that you can find look funny because the video camera taking them is accelerating. And so it makes it look like total chaos in the motion, you know? That's not really going to be a thing in statics, but it will be a thing in dynamics. So it's a good thing to remember. Okay, this simple equation. We are going to do some three-dimensional problems. We're going to do mostly two-dimensional problems. So keep in mind that if you're doing 2D problems, this is a vector equation. So this gives you two equations, like a x equation and a y equation. And if you're in 3D, this gives you three equations. All right, so now every time you use Newton's second law, you need to draw a free body diagram. So free body diagrams. I'll abbreviate these FBD. And why is it called this? Well, it's a diagram, and it represents a single body, a chosen body that you have to be very specific about. And the free means that you remove it from everything that's going on. You remove it from all that, and you replace all that just with the loads that those things represent. Okay? So since I always abbreviate it FBD, a lot of people end up like changing the name of it and calling it a full body diagram or something. Free body diagram, just think of what that free means, you know, like you're replacing everything except the chosen body with just forces. Somebody once called it a free base diagram. Don't call it that. Okay, that is a contract violation if I teach you that. Okay, so for free body diagrams, for every application of Newton's second law, or the moment equation, which we won't get to until we talk about rigid bodies, you need a corresponding free body diagram. And a free body diagram has the following things. So here's what I want in your free body diagram. It doesn't have to be art, you know, but I want a visual representation of the outline of your chosen body. And this outline shouldn't have anything going on inside of it. Like you're not drawing eyes on your people, you're not drawing doors on your cars, any of that stuff. It's just the outline. And then nothing representing anything outside of your chosen body. So you're not drawing the grass underneath your object. You're not, you know what I mean? You're only drawing the outline of your body. The only reason that you're drawing the body at all is to be clear to the person who's looking at it what's included in your chosen object and what's excluded. Okay? You're just dividing the world up into the in crowd and the out crowd. Okay? And then on that outline of the chosen body, you're drawing each load acting on the chosen body. Okay, so what does that include? That includes the weight, the force applied by gravity, which is the mass of the object times 9.81, 9.80655. And then a load for every place the surroundings contact the outline. Or the boundary of the chosen body. Well, really, technically, the weight is one of a whole category of things that could be happening. Field forces, those include magnetism, electrical forces, all that kind of stuff that just depends on an object's position. But in this class, it's mainly going to be the weight. So I've simplified this a little. This represents all field forces. Okay, so what you can do for your free body diagram, things are going to get really complicated looking, but you can simplify it in your head if you just say, okay, here's my outline. Now I'm going to apply the weight to it, a downward force applied by gravity. And then I'm just going to go mentally around the entire boundary, looking for places where the surroundings make contact with that boundary. And at every one of those places, I'm going to have to figure out what the type of load is that contact applies to the body. And once you've done that for every point where there's contact, you know you're done. Your job is done. Okay? So things will look complicated, but stay focused on the sort of simple task. Here's sort of an interesting philosophical thing. So I said that F net is the sum of all forces acting on the chosen body. Okay, so think about my chest. Say that the chosen body is me. Okay, think of all the forces acting on me. There's a whole bunch besides gravity. There are a whole bunch of forces acting on me that are not the outside world acting on the boundary. They're internal things going on, 60 times a second or whatever, like my heart is pumping, and that's creating a force of the blood hitting the, vessel walls and all this stuff. There's all this stuff going on inside. There's things going on inside every cell. So why am I glossing over all that internal stuff when the rule for Newton's second law says add up all the forces, every single force, and it has to be equal to 0? There's a really nice, clean reason that we can do this. And it has to do with a Newton's law other than the second law. Anyone remember what Newton's first law is? That's not the one that applies here, but what's Newton's first law? That's the one that says an object in motion stays in motion in a straight line with a constant speed, whatever the wording is, which basically is just a subset of Newton's second law. But what's Newton's third law? That's the one that matters here. Equal and opposite. So if you have two objects that are in contact with each other, the force that this object applies to this one is equal and opposite to the force this one applies to this one. Okay, so now think about that for each one of the interactions that's going on inside the boundary of your chosen object. This is applying a force to your chosen object this way. This is applying a force to another part of your chosen object this way. Those are equal and opposite, so they cancel out. So the only place that Newton's third law doesn't make forces cancel out is at the boundary. Okay? So that's why we can, I mean, we're really lucky that this is the case. Imagine trying to do physics on a body and having to think about what's happening inside every cell or whatever. It would be impossible. But this becomes a manageable job to only have to worry about the boundary. Okay, so now we've simplified this into the weight and then the contact forces. Those contact forces, I'm going to make a category called joints. These are the contact forces. This is contact between bodies. And there are only 3 types that we're going to need for particle statics before we get into rigid bodies. The first one is cable forces. So forces applied to bodies by cables. And this is always a pulling force. And the rule for a cable force is the force vector is parallel to the cable away from the chosen body. Okay, so for example, if you have a 10 kilogram mass attached to the ceiling by a cable like that, then a free body diagram of the 10 kilogram mass looks like this. There's a weight force acting down. 10 times 9.81 is 98.1 newtons. And now go around the boundary of this mass looking for contact. The only contact is the cable. And so right here, we're going to follow the rules of a cable force, which are parallel to the cable. So that one tells us it's either straight up or straight down. And then away from the body, so it has to be straight up. And we don't know what that is yet, so I'll give it the name T. Okay. And a lot of times these cables will go over pulleys, through pulleys. So if a cable passes through a pulley, I'll call it an ideal pulley. All the pulley does is change the direction of that force, not the magnitude. And we'll do some problems like that. I know you've done that kind of stuff before. Anybody have any questions about cable forces? Then the second joint type for particles is frictionless contact. This is a pushing force. And the rule for frictionless contact is that the force is perpendicular to the surface I'll call it the surface of contact. Toward the chosen body. A lot of times frictionless contact will be indicated by wheels. That's just used as kind of a shorthand to tell you that there's no friction in the problem. So let's say that you have a ramp. And on the ramp, you have a mass. Let's say this is 1 kilogram. So to draw a free body diagram of this cart, you'd have the outline of the body. A weight force of 1 kilogram times 9.81 meters per second squared. So that's 9.81 newtons. And then I'm only going to draw this on one wheel for now because particles, what a particle is something that you're treating as having no length dimension. So everything really is happening at a single spot. So I'm just going to put this all at one wheel. But you have a force vector that's perpendicular to the surface. So it could be down and to the left or up and to the right. And then it's toward the chosen body, so it has to be this way. And, you know, we don't know what the magnitude is. I'm just going to give it a variable name. A common one is normal force for this. So that's a complete free body diagram because now we've gone all the way around and the wheels are the only place that it's contacting the surroundings. The boundary is contacting the surroundings. And then the last one is a friction contact. And a friction contact applies a full force vector. So notice that that is, if you're in 2D, that's 2 components. And if you're in 3D, that's 3 components. And I want you to notice that this is different from how you treated friction in Physics 1. In Physics 1, you broke up friction forces into a normal force and then a friction force that was perpendicular to it. And the reason for that is we often use kinetic friction. And when we use static friction, we wanted to calculate the maximum possible friction force that could be provided. So using the coefficient of friction was helpful. In this case, everything is static, and we don't care about the maximum friction force. We just know that it's contributing to this thing being at rest. So we don't care what the maximum is. So we're not going to break it up into a normal and a friction force. This is actually easier in this class. We're just going to treat it as an unknown force vector. Okay. So as an example, so let's say that we have a ramp. And we have something that's in contact with it with friction. I'll say this is 2 kilograms. Oh, and the other thing, since we're not breaking it up into a normal force and a friction force, remember the tedious trigonometry that you had to do to break things up into a normal and a friction force? We don't have to do that. So there's no reason in statics to use a rotated coordinate system for doing friction contact calculations. Okay, so I'm not going to worry about using a y-axis that's out of the surface and an x-axis along the surface. I'm just going to keep, even though this is tilted, I'm just going to keep using my normal coordinate system. So free body diagram of this 2 kilogram thing. We have the outline. We have the weight force going straight down. So 2 times 9.81 is 19.62 newtons. And then the friction contact, I'm going to write something in the direction of our x-axis, something in the direction of our y-axis, and I'm going to represent this vector with a vector variable, and I'll call that just r for reaction force. And it's a vector, it has both of those two components. And then when we go to Newton's second law with this r is going to be equal to, there'll be an x component and a y component in our equations. Okay, so now let's spend some time doing some problems. So I'm going to write this problem up. I'm going to give you some time to think about it. I notice no one's sitting right next to each other, but I do think it's helpful. You don't have to do this, but I think it's helpful to compare what you're doing to other people, try to talk through it with people. So if you feel up to it, work together with someone near you. And then after I've given you some time to think about it, compare answers, that kind of stuff, I'll come back up here and I'll go through it and you can compare what you've done to what I do. And that way you can sort of catch misunderstandings if they come up. Okay? So the first example, let's say we have a ramp that makes an angle of 5 degrees with the horizontal. And there's a cart on it that makes frictionless contact with the surface. That's what the wheels mean. Let's say that this has a mass of 5 kilograms. And this cart is held up on the ramp by a cable. So first, let's do this sort of in pieces. I want you to draw a free body diagram of the cart. And if you get confused about it, it really is about just going up here and following the rules here. Yeah, where there's a pulling contact, go to the rules for a pulling contact. Where there's a frictionless contact, go to the rules for a frictionless contact, and that'll tell you everything you need to know about drawing your free body diagram. So, okay, go ahead and draw this, and then I'll put a couple more parts to this up. Okay, so I'm going to draw the closed outline. There's a weight force down that's equal to 5 times 9.81, so that's 49.05. And now I'm going to go around the boundary. In 2D, going around the boundary is just going around the outline. In 3D, you have to sort of imagine the whole three-dimensional outline, that whole surface. But But I'm going to start at the bottom, and the first contact is with the wheels, contacting the ramp. Again, I'm going to just lump it into one place. And so this is a frictionless contact, which means I'm going to follow the rules for a frictionless contact, perpendicular to the surface, toward the chosen body, and give that variable a name. I'll call it N for normal. But if you like to feel like you control your own fate and I'm not the boss of you, you can call it X or whatever. It's just a variable. And then if we keep going around counterclockwise, the next contact we get to is the cable. Okay, and so here we use the rules for a cable. It's parallel to the cable, away from the body, and I'll give that the variable name T for tension. So the magnitude of a pulling force from a cable is called a tension. Okay. And then if you keep going around the outline, there's no more contact with the surroundings, and so we're done. Anybody have any questions about that? Okay, now we're going to do the calculation, and this is going to require representing these as force vectors. And I'm going to use, I didn't say this, but I'm going to use a coordinate system that's oriented like this. It didn't matter yet, but it's going to matter for the calculations. And let's calculate the force vector applied to the cart by the incline. And let's calculate the cable tension T. So that's just the value of that variable T. And then fourth, let's calculate the force vector applied to the cart by the cable. Okay, so calculating the cable tension and the force vector, those are obviously similar related things, but they're not the same thing. Okay. So go ahead, take a few minutes and see if you can go through this calculation, and then I'll go through it, answer questions. Okay, so the basic idea is every force that appears in the free body diagram is going to be a force vector on the left side of Newton's second law. Okay, that's what we're going to do. And I mean, probably the trickiest thing about it in this case is representing those arrows as components of a vector, each one of those. So I'm going to try to be sort of systematic about how I do these calculations. So first of all, the weight force, so I'll call it this mg weight force vector. That's just straight down, so that's in my negative y direction. So I'm going to write that as 0, negative 49.05 newtons. But now these other two are in incline, so how am I going to do those? So I'll do them one by one, and I'm going to draw out the coordinate system. The x-axis is along the horizontal. We know that that cable force, it's parallel to the ramp, right? And the ramp is 5 degrees above horizontal. So we know that this cable force is in this direction where this is 5 degrees. And the magnitude here is t. Okay, so now that we have this is just like one of those vector problems that you did where we know the magnitude is t, and we're just multiplying that t by a unit vector. And since this is in 2D and we're given a reference angle, we can just use cosine and sine. So the counterclockwise angle from the positive x-axis here is positive 5. And so this vector is going to be t times the cosine of 5 degrees, t times the sine of 5 degrees, and I do not know those off the top of my head. Cosine of 5, sine of 5. Okay, so we got 0.996 t and 0.087 t. Okay, so that's for that cable force. Anybody have any questions about that, how I did that? And then we'll go down to the next one. Okay, and it's not as clear what the angle is to this n force vector, but you can always sort of piggyback if you know an angle to something, and then you know the angle from that something to the thing you want. You could bounce around several times and use that technique. So let's do it this way. Well, what do we know about this normal force? We know it's perpendicular to the vector that I just drew here, right? So I'm going to first draw a reference vector like this, and then I'm going to draw the vector we want like this. And the thing is, we know that these are 90 degrees apart. Okay, so I'm going to go my theta. Then I'm going to start at the positive x-axis. I'm going to go counterclockwise, so positive 5 degrees. Then I'm going to go counterclockwise another 90 degrees. And so my theta is 95. And so that force vector is n times cosine of 95 degrees, and then n times sine of 95 degrees. And so that is negative 0.087 n and positive 0.996 n. Okay. You also could do that, set up right triangles and just think about the quadrant it's in. But these now are our 3 force vectors in this red coordinate system. And since those are the only force vectors, now I can set up Newton's second law. Oh, one thing I wanted to mention, it can get a little confusing using capital N as a variable and also using capital N as a unit. And to make it a little less confusing, when I use it as a variable, I'm always going to put the little fancy hat and shoes on it. And then when I use it as a unit, it's just going to be a plain capital N. Okay, so Newton's second law says, I'm just going down the list, 0, negative 49.05, plus 0.996 t, 0.087 t, plus negative 0.087 n 0.996 n Our free body diagram has three forces. I have three forces here, so that's everything. I didn't miss anything. And Newton's second law for static says that it's equal to 0. Okay. Well, now we have a system of equations to solve. I think the next lecture video I give you is going to tell you a really nice way to do this on your calculator. But with two equations and two variables, it's not too hard to just do it by substitution or whatever other technique you like. Let's see. The first one says 0.996 t is equal to positive 0.087 n. And the second one says 0.087 t plus 0.996 n is equal to 49.05. So here t is equal to I'll keep a bunch of, so this is 0.0875 times n. And so now we can substitute that into this one. And we have 0.087 times 0.0875 n. That's going to be something tiny. Plus 0.995 n is equal to 49.05. This was 0.996. I don't know why I wrote a 5 there. And so n is equal to 48.873 newtons. We're just solving for all the variables now, so we can go up here to this equation. Like, what equations can you use to solve this now that you have n? If you didn't make any math mistakes, everything you have up here is true, so you can go to any one of these equations. This is the simplest one. So we'll go 48.873 times 0.0875, and you get the t is equal to 4.276 newtons. Okay. Well, now we've solved for the variables. Let's go back and refresh our memory on what I asked for in this question. Okay. I did ask for t, so that is an answer. I did ask, like, C, what I asked for here was I asked for the cable tension. So this already is an answer. But I didn't ask for n. Instead, what I asked for was the force vector applied to the cart by the incline. Okay. So let's go back up here to down here to Newton's second law. and figure out which one of these vectors represents the force applied to the cart by the incline. Okay? The answer is this one. And so in order to come up with the force vector applied to the cart by the incline, we have to just plug our n value into this. Okay? So I'll write this as the force on the cart by the incline, and it's equal to negative 0.087 times 48.873 for the x component. For the y component, it's positive 0.996 times 48.873. And so we got negative 4.252 for the x component. For the y component, .678 units are newtons. And so that force vector has a big positive y component and a small negative x component, which makes sense when you think about this force as being in the direction of that n in our free body diagram. So that's an answer. And then the last thing I asked for was the force vector applied to the cart by the cable. Newton's second law, we've already listed out all the forces applied to the cart by various things. So we just have to identify it, and this is the one we want. That's the force vector on the cart by the cable. So the force on the cart by the cable is 0.996 times the t that we calculated, 4.276. And then for the y component, it is 0.087 times t, 4.276. And you get 4.259, 0.372. So a big positive x component, a small positive y component. And if you look at that cable force, the direction of that cable force, that makes sense. So this is newtons. Anybody have any questions about that process? Okay. Let's do another one. Each more diabolical than the last. This actually, I should have done these in the reverse order if I wanted to do that. This is less diabolical than the last. Okay, so this time, let's say the angle of this ramp, it's the other direction. The slope is the other direction. And the angle is 10 degrees. And this time we have a friction contact, so I'm not going to draw the wheels. And let's say this mass is 0.5 kilograms. And let's say that at this instant, the box is sliding down the ramp. With a constant speed. So first, draw the free body diagram of the cart, of the box, I guess. And ask yourself, would anything be different if this was at rest on the incline? And I guess let's start with that again, and then we'll go in and do some calculations based on the free body diagram. All right, so I'm going to draw the outline. I've drawn these, by the way, heavily exaggerated, the angles. If you look at that, that's nowhere near 5 degrees. This is nowhere near 10 degrees. But for small angles, I feel like sometimes it helps to exaggerate the angle a little bit in your pictures, because then you don't get confused about assuming that things are parallel or perpendicular that are not, in your free body diagram, you'll be happy if you make it clear to yourself what is and what is not parallel and perpendicular, Okay, so the first thing is the weight force. 0.5 times 9.81 is 4.905. And now going around the boundary looking for contact, the only place is where it contacts the ramp. And so that's a friction contact. So it's going to have an X and a Y component. So I'm just going to draw vectors in the X and Y direction. And I'm going to give it a name. I guess I'll call that the R vector. There are no more contact points with the boundary, so we know we're done. Okay. So now take a few minutes and see if you can calculate. Oh, I haven't told you what to calculate. See if you can guess what I'm going to ask you to calculate. Oh, and then before we get into that, is anything different with this problem? So I said that this is sliding down with a constant speed. Is anything going to be different about this problem if that is at rest there? It seems like it would be.
But it's not accelerating.
That's right. All we care about with Newton's laws is whether there's acceleration or not. We can use the rules of statics as long as acceleration is 0. So the whole process would be exactly the same in either case. Okay? All right, so this time let's calculate the force vector on the box by the incline. Okay, go ahead and quickly. So Newton's second law, we have to represent each of these drawn forces as components. We have the weight force of 0, negative 4.905. We have that R force vector that I'll represent as Rx, Ry. We don't know what either one of those components are. And it's moving, but the acceleration is 0, so this is still equal to 0. And now we just have two equations. We can solve for Rx is equal to 0. Ry is equal to 4.905. And so the force on the box by the incline is just 4.905. Okay, so even though this is on an incline, the force here just happens to be exactly, straight up. What we didn't do, so why is this so much simpler than a static friction problem from Physics 1? What we didn't do is break it up into what component is the normal force and what component is the friction force. We don't care about that for our purposes in this class. And so we didn't have to worry about changing the orientation of the coordinate system, all that stuff. That's why this was so much simpler. What if you did want to calculate the component of this that's the normal force and the component that's the friction force? You could do that with a dot product with projections. So you could go let's just calculate what's the normal force. Well, you need a unit vector that's straight out of the surface. That's what we're trying to figure out, is what's the component of this force vector that's parallel to this. And you could do that in steps by saying it's negative 10 degrees to get here, and then 90 degrees to get here. So our theta is negative 10 plus, because we went clockwise 10, then counterclockwise 90. So that's 80. And so that unit vector is cosine of 80, sine of 80, which is 0.174, 0.985. And now we could take the dot product of this with the vector that we got. And that's 0 times 0.174 plus 0.985 times 4.905. And you get that the normal is 4.831 newtons. And you could use a similar idea to come up with the friction component. In this class, we don't really care about that, but I think there is actually one homework problem where it asks you to do that. So that's how you do it. Okay, let's do another one. Let's say we have a pulley attached to the ceiling. And the cable that goes over the pulley, one end is attached to the ground, and the other one is holding up a mass of 3 kilograms. So first, draw a free body diagram of the 3 kilogram. I'll give you a minute or two to draw that. Okay, so for a free body diagram, we have the weight down. 3 times 9.81 is 29.43 newtons. Then the only other place where the surroundings contact the boundary is at the cable. So that force is parallel to the cable, away from the body. And I'll call that T. And now I want you to calculate 2 things. I guess 3 things really. Calculate the cable tension. Calculate the force vector the cable applies to the mass. And then last, calculate the force vector the cable applies to the floor. Okay, so take a few minutes and see if you... we only have 2 forces to deal with when we go to Newton's second law. Downward force for the weight, and then an upward force for the cable. So that's 0 positive T. Set it equal to zeros. The x equation doesn't give us anything useful. The y equation says T is equal to 29.43. So that's the answer to part B. And now for part C, we want to calculate the force vector applied to the mass by the cable. If you look in Newton's second law, where we've already written all the forces applied to the box, this is the one we want. And so we can just plug T in to that vector, and we get that the force on the box by the cable is equal to 0, 29.43. Okay, and then the last thing I asked for was the force vector applied to the floor by the cable. Okay, so how are we going to get that? Well, we know that all a pulley does is change the direction of force that a cable applies to bodies attached to it. So if we're looking for the force vector the cable applies to the floor, We know what the magnitude is because it's the same cable, it's just gone through that pulley. What about the direction? Well, if we think about a chunk of the floor, and we have this cable attached, the rules for a cable force are that it's parallel to the cable, away from the chosen body, which in this case is the floor. And so this force is going to be up. So this is parallel to the cable. Away from the chosen body. And so it's like this with a magnitude of 29.43. And so the force on the floor by the cable is equal to 0, positive 29.43. Well, the same as it was for the mass. Any questions about that one? Okay, now I want to do one last one, and this is about pulley advantage. And maybe some of you had saw this in Physics 1, but I would definitely guess not all of you did. And this is something I remember being confused about when I first took physics in high school, because I'd heard that pulleys had this ability to reduce the force you needed to lift an object. But then when we learned about pulleys in the class, he said, the teacher said that all a pulley does is change the direction of the force that the cable applies, So how can those both be true? And it turns out that it's not the pulley that makes it easier to lift something, but you can take advantage of pulleys in a way that does reduce the force required to lift an object. And that technique is used with things called block and tackles in shipping yards and storage places all the time. And so pulley advantage is a way to reduce the force required to lift an object. And the way you do it is you have a pulley that's attached to a support structure. I'll do it to the ceiling. And then you have a second pulley that the mass is supported by. So this pulley is holding the mass that you're lifting. Let's say this is 20 kilograms. And then the cable goes over the two pulleys. The mass that you're lifting, the cable goes under that pulley and then attaches to the ceiling. And then the other end, since this is statics, this would be connected to the motor that lifts it, or since it's statics for us, we can just imagine this attached to the floor. And we want to calculate the tension in this cable. Okay. Well, if instead of doing this, so say that I had skipped this whole thing with the second hanging pulley, and I just connected this 20 kilogram mass to the left side of this cable here. So we just had one pulley attached to the ceiling, the cable attached to the ground, went over, and then held up the weight. Can you picture what I mean there? Then the tension in that cable would be exactly what you expect, the weight of this. So 20 times 9.81, 196.2 newtons. Okay, but we're going to see that in this configuration, the tension in the cable is much less than that. Okay, so how are we going to do that? The real trick here in doing this calculation is coming up with a good thing to isolate. Okay, a good body to take as your chosen body. And anything that you can completely enclose in, think of shrink wrap or something, even mental shrink wrap, you could go through things as long as this thing is continuous the whole way around. You can make that your chosen body. So what we're going to make as our chosen body is all the cable, and I want to emphasize there's cable going under here, right? And what I am going to isolate as my chosen body is all of this in the red outline. Okay, so notice that means my chosen body includes some cable that goes underneath the pulley. All right, and now let's think about draw a free body diagram of this. Okay, so if I draw a free body diagram or draw an outline of all the stuff in the red, it looks like this. There is a weight. We're using ideal pulleys right now, which means it's frictionless, massless. So the only mass contributing to the weight of everything in here is the 20 kilograms. 20 times 9.81 is 196.2 newtons. And now we'll go up to these two. So notice there are two places now where the surroundings contact the boundary. The two little bat ears, the cable contacts the boundary here, and the same cable contacts the boundary here. And at both of those two places, we're going to follow the rules of cable forces. So at the one on the right, the rule of cable forces says parallel to the cable away from the chosen body. And the magnitude is that cable tension T. And then at the one on the left, same exact thing, parallel to the cable, away from the chosen body. It's the same cable, so it has the same force T. And now this is everything, so we can go to Newton's second law. We have these two things in the positive y direction, so 0t plus 0t plus 0, negative 196.2 is equal to zeros. The x equation doesn't give us anything, but the y equation says 2t is equal to 196.2. And so T, the tension in that cable, is 98.1 newtons. So this configuration has cut the required tension in that cable to hold this up in half. It kind of has the feel of one of those things, I think, where like a trick, like where did I violate something? But it really works. It's easy to ring, like in the physics lab, it's easy to take a pulley and set it up this way, and you can feel it. It really cuts the weight in half. There is sort of a question of like, doesn't it violate conservation of energy in some way? It feels like it would. Like suddenly you can just lift this same thing by applying half as much force. But there's a reason that it doesn't. So now we're getting away from statics for a second and thinking about dynamics. So imagine that this isn't attached to the ground, it's being held by your hands or by a motor or something. Okay. Why haven't we reduced the energy of lifting required to lift this, even though we've cut the force in half? And the answer is, notice that if you wanted to lift this an inch, okay, you'd have to remove an inch from this side of the cable and an inch from this side because of symmetry. That's 2 inches that have to be added to this length of cable. And so you're applying half the force, but in order to lift this an inch, you have to apply that force for 2 inches. And so the work is the same in both cases. Okay. If it's just static, there's no energy used at all. The thing isn't moving. Let's do one more problem. Okay, so let's say that we have a 20-degree incline. And we have a frictionless contact with a cart. Let's say that this is 1 kilogram. And a cable attaches to the cart here and attaches to an unknown mass m here. What mass m is required for equilibrium? Okay, so take a few minutes. So in a problem like this, you're going to have to isolate each one of these at some point. It doesn't matter which one of these two bodies you do first. I'll start with the 1 kilogram. If I don't have a reason to do one over the other one, I seem to work from left to right, so it's pretty arbitrary. So we have the weight force of 9.81 newtons down. This is a frictionless contact, so the rule says perpendicular to the surface of contact toward the chosen body. And then the only other place that there's contact is the cable, and the rule says parallel to the cable, away from the body. And I'll call that T. And we're going to assume that this is in equilibrium. So we can use the rules of statics for this. So Newton's second law says 0, negative 9.81. The angle from the, I'm using this, we've used the same coordinate system orientation all day today. I'm going to use it again here. So to get from the positive x-axis orientation to the orientation of t, if you put the tail at the origin, that's a 20-degree angle. So this is going to be t times cosine of 20, t times sine of 20. And then the last one is that normal force. That is going to be 110 degrees. So we have n times the cosine of 110, n times the sine of 110, that's equal to zeros. I can rewrite this as 0, negative 9.81. And that is 0.940 t, 0.342 t. And then for n, we have negative 0.342 n, positive 0.940 n. Is equal to zeros. And we have a system of two equations for two variables. So 0.940 t is equal to 0.342 n. So n is equal to 2.7485 t. And then I'll plug that into the second equation, which says 0. So I'm taking this and taking this. So 0.342 t plus 0.940 times n, which I'm substituting in this thing, 2.7485 t, is equal to 9.81. And I get that t is equal to 3.353 newtons. Okay, so that's the tension of that cable that's required for this to be in equilibrium. Equilibrium, remember, means it could be at rest, but it also could just be moving with a constant velocity. And now we'll go to a free body diagram of the mass m. Okay, so we don't know the mass. We're trying to calculate that. So the weight force is going to be 9.81 times m. And then since this is the same cable passing over a pulley, we know that the cable tension is going to be the same, just the direction is going to be different. So the rules for the direction are parallel to the cable, away from the body. And the magnitude is 3.353. And now we'll go to Newton's second law. We have 3.353 plus 0, negative 9.81 m is equal to zeros. The x equation doesn't help, but the y equation says 3.353 is equal to 9.81 m. And so m is equal to 0.342 kilograms. Anybody have any questions about that? Okay, well, that's all for today. And look on D2L in a little bit, and there'll be some problems up doing this kind of thing. And see you later. Oh, did you notice on D2L, we had to switch the room number that office hours are in? It's in the mechanics lab instead of the electronics lab now, so S1324.